Hello, class. I want to cover the next section, which is 2.8, and it's the derivative as a function. So we've already talked about this definition of the slope of the tangent line, or you can think of it as the instantaneous rate of change, because that's the same thing. Or we can think of it as, if we're talking about position function and velocity, we can also think of it as instantaneous velocity. So we should already know this. And this is just, this is like definition 2. So there was a definition 1. This is just definition 2. So it could just as well be definition 1 here. So if we replace the a variable with x, we get this just written in another form. And what it is it's the derivative of a function f of x, but we're looking at it now as this derivative is also a function of x. So f of x is a function. It is the slope of the tangent line to the graph of x of f at the point x f of x. And so I'm sorry, this is supposed to say f prime x. I think I said the wrong thing. F prime x is a function. F prime x is a function. It's the slope of the tangent line to the graph of f at the point x f of x. So just some other notations for this, if I can get it straightened up. F prime x, you'll see it, and we'll use this notation. Y prime x. Just one second. And so anyways, these are just different notations for f of x. And so it could say y prime, that's y prime. We will look at that notation. It could say dy dx. We'll also look at that notation. Or df dx or d dx of f of x. We don't use these very much in calculus 1 or 2. But those are some other notations you could see in a different course. But we do use f prime x and y prime x. We do use dy dx, and we use these other two sometimes as well. So, I'm sorry, my Alexa keeps thinking I'm talking to her, and so I have to keep telling her to stop. So hold on just a minute. Okay, I just unplugged Alexa so she wouldn't be going crazy thinking I was telling her to do something. Anyways, let's look at some more stuff here. So let's look at an example. Now this example, we actually saw some like this last time. But what I want to do is I want to use the definition of the derivative to find f prime x. So f of x in this case is equal to the square root of 3 minus 5x. And so I'm going to use this definition. I could use the other definition, definition 1, but I'm going to use this one this time. Let me move over just a little bit. I'm sorry that I'm always having to play around with this thing. Back when our school still used the smart board, it was a lot easier, but you know, they chose not to do that anymore. And that's all I'm going to say about that. Okay, so I'm going to use this definition. So if I use that, then it's going to look like this. F prime x equals the limit as h goes to 0 of the square root of 3 minus 5 times x plus h minus the square root of 3 minus 5x. And that's all going to be over h. Now that's just the setup, because this is just where I have x, I'm putting x plus h. And then this is just f of x. So that's just the setup. Now, if we were in class, I'd stop and say, who remembers how to simplify this? Because remember, we don't want to substitute in an h or 0 for h at this point, because we know that would be undefined. What we need to do are some algebra techniques so that we can get this h in the denominator to cancel. That's what's keeping us from substituting. So do you remember what we do? Well, we need to remember this, that when we've got two terms like this in the numerator, we want to multiply by the conjugate. Now, that doesn't matter whether they're square roots or not, but if we've got two terms like this, so let's see what we're going to get when we do that. So we've got the square root of 3 minus 5 times x plus h. And then the conjugate would have a plus sign right here. And everything else is going to be the same. I'm going to move that h up just a little bit. And then I'm going to be multiplying by plus the square root of 3 minus 5x. And then, because remember, when we do this, something special is going to happen. But also remember that whatever you multiply in the numerator, you have to also multiply by the same thing in the denominator. And, you know, it's the change, it's this sign that changes so that we have the conjugate here. Then when we multiply, remember, it's kind of like multiplying difference of squares. What's going to happen is we're going to get the square root of 3 minus 5 times x plus h. And that's going to be squared because we get the square of the first term minus the square of the last term. And then in the denominator, we've just got all this stuff. Now don't distribute, just leave it like it is, because remember, we want to cancel the h. So we just write it again. Okay, now what happens when we square the square root? They cancel each other out, don't they? So we've got the limit as h goes to 0. And we've just got a 3 minus 5 times x plus h. And we've got minus a 3 minus 5x. And then we've got our stuff in the denominator. Okay. See what we got here. So what we're going to do now is we're going to distribute all of this. So I'm going to have, let's write it right here, limit as h goes to 0. I'm going to have a 3 minus a 5x minus a 5h. And then I'm going to distribute the minus sign. So I have a minus 3 and plus a 5x. And then I've got all that stuff in the denominator. We're wanting this h to cancel. No need to distribute or anything in the denominator right now, or maybe ever in this problem anyways. So let's see what's going to cancel. So my 3 is going to cancel with my minus 3, my minus 5x with my plus 5x. So I have the limit as h goes to 0, and I've got the minus 5h over the stuff in the denominator. And we see that we're going to be able to cancel the h now. Okay, now finally cancel the h. And then we're going to substitute in h is going to 0. So we're just going to go ahead and substitute that in. So we have a minus 5. And then in the denominator, we have the square root of 3 minus 5. H is going to 0 right here. So this h is going to 0. That's an h right there. So that'll just be times x right there. And then we also have this other square root of 3 minus 5x. So we can combine these two in the denominator. So I have minus 5. And notice I keep writing limit until I finally substitute in 0 for h. And that's important that you do that. Okay. And so we've got minus 5. And then what I've got in the denominator, I've got 2 of these square roots of 3 minus 5x. And that's equal to the derivative, f prime x. Okay, now what is the domain? F of x. And this was f of x. Okay, so if you remember back from college algebra, that the 3 minus 5x has to be, if it's under a square root symbol or any even root, even indexed root, then it has to be greater than or equal to 0, as long as it's not in the denominator. So that means that minus 5x has got to be greater than or equal to minus 3, or that means that x has got to be less than or equal to 3/5. Okay, so in interval notation, I'll write down here. Or an interval notation, that's going to be, it's got to be less than, so from negative infinity up to 3/5. Like that. Now, what is the domain of f prime x? Let's see, it's a function too, as well. So let me put a little thing here so this will look better. Well, if you look at f prime x, it's equal to minus 5 over 2 times the square root of 3 minus 5x. So the square root of 3 minus 5x is in the denominator. So what that means is that x has to be less than 3/5. It can't be 3/5 because if it is 3/5, this denominator will be 0. So in interval notation, it would be from negative infinity to 3/5 and not including 3/5. So anyways, that's talking about that function f of x and its derivative f prime x, which is also a function. Okay, what else we got? Talk about this page for a second and we'll move on. Function f is differentiable at a. And this is a new term that we're learning. If f prime a exists, then we say it's differentiable at a. It is differentiable on an interval, on an open interval from a to b, or from a to infinity, or minus infinity a, or minus infinity and to infinity, if it is differentiable at every number in the interval. So that's what it means for a function to be differentiable. Now, one thing that's true, and we're going to talk about this some more, you know, there's a lot of functions that have the limit exist. And then in order for a function to be continuous, the limit has to exist. So what this means is like the limit as x goes to, let me write it out a little bit better, or put it right here. I mean, for the limit to exist, that just means the limit as x goes to a from the plus side equals L, and the limit as x approaches a from the minus sign that equals L. That means the limit exists at a. The limit exists, and we'll say at a. Now, to be continuous, it has to be more than that. It has to be that the limit as x approaches a of f of x equals f of a. Because so that implies that the limit exists and the function is defined and that they're the same thing. Now, there's an even smaller set that's a subset of continuous. Let me make it look like a subset of continuous. And this is differentiable. Sorry, I didn't plan out how to space that. So what I'm saying is, in order to be differentiable, it must first be continuous. And to be continuous, you know, the limit has to exist. So all of this has to be true. So differentiable is, it's even more special than continuous, which is even more special than the limit existing, I guess is what I'm saying. Or in other words, being continuous is a prerequisite for being differentiable, and the limit existing is a prerequisite for continuous. So limit existing is a prerequisite for being differentiable. Okay, so the next thing I want to talk about is how can the function fail to be differentiable? So what would make a function not be differentiable? Well, what would make it not be differentiable is if that limit, that's the definition of the derivative, doesn't exist. I mean, that's really what it would be. Okay, so this is an example of a function that is differentiable at a point. Now, you know, there's other functions that are differentiable maybe at infinitely many places, but this one is differentiable. It's differentiable at everywhere except one point. So maybe you could guess that it's going to be that point. But why would that be true? Okay, so where is f of x equals absolute value of x differentiable? Or not differentiable. Or maybe I should say and not differentiable. Okay, so let me move on down a little bit. Okay, so that's what it looks like right there. It looks like the absolute value function looks like that. So by definition, of what the derivative is, f prime x would be, you know, this is just the definition. The limit as h goes to 0. And then if we're using the absolute value function, it would be the absolute value of x plus h minus the absolute value of x over h. Because remember, it's f of x plus h. That would be f of x plus h minus f of x over h. Okay, now let's look at some cases of this. When x equals 0, then f prime of 0 equals f, or I need the limit here. Shame on me. There. the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. Now, equals the limit as h goes to 0 of, in this case, the absolute value of h minus the absolute value of 0, which is just 0 over h, which is just the limit as h goes to 0 of the absolute value of h over h. Now, if we look at this limit as h goes to 0, if h is approaching 0 from the negative numbers, then the absolute value of h over h, well, h is negative. This is all slanted to y'all. Hope not. I'm not making it easier. So if h is negative, because h is coming into 0 from the negative side, then the absolute value of h is the opposite of h, because h is negative. So that would be minus h over h, which would be minus 1. Okay? And the limit as h goes to 0 from the plus side of the absolute value of h over h, well, if h is positive, then the absolute value of the number is the same as the number, which would be equal to my limit right here. Without the word limit. Erase. And so that's going to be h over h, which is going to just be a positive one. Okay, so notice this. When we're coming in from the left, h is coming in from the left of 0, we get minus 1. When h is coming in to the right of 0, we get 1. And these two are not equal. So that means that f prime at 0 does not exist because the limit doesn't exist. Because the definition, which is not the limit at 0, but the limit that's the definition. The definition, which is the limit as h goes to 0 of f of x plus h minus f of x over h, that's the definition. It does not exist. Okay, so it does not exist. So, and if you look at the function over here, again, right, the slope of the tangent line here is 1. The slope of the tangent line here is minus 1. Now, if your function is linear, like this side is linear and this side is linear, actually over here, the function is f of x equal x. Then over here, the function is f of x equal minus x. And they're straight lines. But, I mean, each side is a straight line. But if you, if it's linear, the slope of the tangent line is just the slope of the line. So actually, my derivative looks like this. It's a piecewise function. F prime x equals minus 1 if x is less than 0. And it's equal to 1 if x is greater than 0. And if x is equal to 0, it does not exist. Now, if you graph this, it's going to look kind of like this. It's going to be, say this is 1 and this is minus 1. So it's not going to exist here, but it's going to be at 1 when x is positive, and then it's going to be at minus 1 when x is negative. So that's the one. Oh, and this should be an open circle. Okay, so if you see a function and its derivative looks like this, it might be an absolute value function. Okay, so that's an example. If you look at this, that's an example of why or where a derivative wouldn't exist. And notice it's right here at this sharp corner. And whenever a function changes abruptly like that, so it really changes at this one point, it changes, abruptly, then its derivative is not going to exist. So what we're saying then is this. Okay. That if f is differentiable at a, then f is continuous at a. We already said that, okay? Now, when I drew that set picture, the converse is false. A function may be continuous at x equal a, but not differentiable at x equal a. So from the previous example, like if we look back, and I'm not going to turn it back and mess it up, but if you looked at the absolute value, it's supposed to be like that, 0. F is continuous at x equal 0. It's continuous there. There's not a hole or a gap or anything like that, but f prime of 0 does not exist. Okay, so a function may be continuous at x equal a, but not differentiable at x equal a. So the ways that a function could be not differentiable is summarized right here. There's a sharp corner. There's a sharp corner, like right here. There, and all of these are when f prime of a does not exist. So at a corner, also at a discontinuity, so right here, this is an open circle, and whether it's an open circle, but this is closed circle, but you see there's a gap there, there's a discontinuity. It may be a jump discontinuity, it may be a vertical asymptote, but there's a discontinuity because remember, in order to be differentiable, it's got to first be continuous. And then the other way is when you have a vertical tangent line. So remember that the slope of a vertical line is undefined, if you remember back from college algebra. So, I mean, the derivative would be the slope of the tangent line. So this is a vertical tangent line. So the slope does not exist here because it's a vertical line. Okay, so those are the 3 ways you've got to remember. Those are the 3 cases. You got to remember this. That a function will be not be differentiable if it's got a sharp corner or where it has a sharp corner, where it's discontinuous, and where there's a vertical tangent line. Okay, so let's look at this next example, which is going to have a graph. And the graph of f, so this is f of x here, is shown. and state with reasons the numbers at which f is not differentiable. Okay. So let's just start going left to right. I just really need to get better at this. I'm sorry. So you see right here, and then we want to say where it's not differentiable, and let's also state where f is discontinuous or not continuous. I think I got it. Now, so if we're going left to right, that's -1, -2, -3, -4. So at x equal -4, and we could just do it like this. We could say whether, where it's not continuous. It's not continuous, is it? So if it's not continuous, then it's automatically not differentiable. Because remember, it has to be continuous first to be differentiable. So at x equal -4, it's neither one. Okay, and then the next place we come to is x equal -1. The next place where we have something going on, there's a sharp corner right there. Okay, so that means at x equal -1, it's not differentiable. And I'm just going to abbreviate here. Okay, and then the next place that something's going on is here at x equal 2. Now, we've got a vertical asymptote right here. It might not be drawn in, but it is a vertical asymptote. I'm just going to say VA for vertical asymptote. So it's not continuous if it has a vertical asymptote, and then it's also not differentiable. And then the last place that we have something going on, and sometimes it's kind of hard to tell whether it would really be a vertical tangent line or not, but at x equal 5, that's at 5, that is a vertical tangent line, not a vertical asymptote, but a vertical tangent line. So it is continuous. It's not discontinuous there, but it is not differentiable. Okay, so like on a test, I might give you a picture and you're supposed to go through and tell me where it's not continuous and where it's not differentiable. Kind of like this example. You can look at it for a minute like that. Okay, see what else we got here. Okay. The next, we're going to talk about velocity and acceleration. So, look at this. Okay, so if f is differentiable, then the derivative f prime is also a function, and f prime may also have a derivative. We call this f double prime. So right there, that's f double prime. Call the second derivative of f. We can think of the second derivative as a rate of change of a rate of change. Okay, so for the best example is this that we use a lot. So say that s of t is the position function of an object at time t. A lot of times we use s of t. V of t is the first derivative of the velocity function, and that's velocity. I'm sorry, I said that wrong. V of t is the first derivative of the position function, and this is the velocity function. A of t is the first derivative of the velocity function, but the second derivative of the position function, and this is the acceleration function. And then J of t is the first derivative of acceleration, the second derivative of velocity, and the third derivative of the position function. And it's called the jerk. And it has something to do with cars, but don't worry about that. But there is actually an application for it in the real world, but I don't really know much about it. So now let's look at this example. So we've got two functions here. The red graph is f of x. So red is f of x. And the black graph is f prime x. So the black is f prime x. Now, what we're trying to do here is see some similarities between, or not similarities, but relationships between the graph of a function and the graph of its derivative. So let me go some more because I'm going to ask some questions. So it says, let me see the whole thing. Okay, so it says on what interval is f increasing and on what interval is f decreasing. So remember, the red is f. So it's increasing on, and this graph is not, it doesn't stop exactly at 1. Like if you look at the red, it stops at, that's like 1.1 over, and whatever it is up, I guess it's 2 up. Okay, so this function is increasing, so the red from here to here. Now, where is it decreasing? It's decreasing on minus infinity to 0 and 1.1 to 2. Okay, so the red is decreasing here, and increasing here. So that's f of x. Now, then the question is, on what interval is f prime positive? Okay, and then where is it negative? Where is f prime negative? So if we look at where it's positive, so the black function is f prime. And a function is positive when it's above the x-axis. So where it is positive is on the interval from 0 to 1.1. And where it is negative, and this is f prime, where it is negative is from negative infinity to 0 and on 1.1 to 2. Okay, so you see what's happening. Where f is increasing, f prime is positive. Where f is decreasing, f prime is negative. Okay, and that's always going to be true. So when I look at this, f is decreasing, f prime is negative. Then f is increasing to right here, f prime is positive to right here. Then f starts decreasing again, and f prime is negative again, okay? Now, where does f have a local min? So we look at the red graph and we notice that it has a local min right here. So there's a local min at x equals 0, and there's a local max at x equal 1.1. Then where is f prime equals 0? Well, let's look at the black. Where is it equal to 0? At x equals 0, right here. And then where's it equal to 0? Again, where is the black function equal to 0 again? And at x equal 1.1. So notice that where we have a local min, that f prime is equal to 0, and where we have a local max, f prime is equal to 0. So what we call this, if we look at the black function, which is, yeah, there's a local, or no, that's not what I want to say here. This is what I want to say here. Not that, not. Right here, this is where we've got a local max, and the tangent line right there is a horizontal line. And if you remember back from college algebra, what's the slope of a horizontal line? It's 0, okay? And then likewise right here at this local min for f, the tangent line is horizontal. Okay, so, and then the slope of the tangent line would be 0. So whenever we see a local max or a local min, if the derivative is defined, then the derivative will be 0. It's possible the derivative isn't defined there, like with the velocity, with the absolute value function. The other thing is, like here, where this function is decreasing, the original function f of x is decreasing there. Well, what's the slope? Like the tangent lines would be, like little lines. I can't draw them in because it's so small, but they would be little tangent lines here, and they would be decreasing. They would have negative slopes. So the slope of the tangent line is going to be negative where the function is decreasing. It's going to be 0 when you have a local min or max where it changes from decreasing to increasing or vice versa, unless the derivative is not defined. And then once the function starts increasing, the slopes of the tangent lines are going to be positive. So, it's like m is negative right here, m equals 0 right here, and then m is positive right here. So anyways, that's how it works. And then let's see, got just one more example here, but this is kind of interesting and kind of funny. I think it's kind of fun. Just imagine kind of like a game. But anyways, this question, we want, and we've got some functions in graph, and then we've got some derivatives graph. So these are the functions. So we want to match the graph of each function with the graph of the derivative. That's better. So these are the functions right here. And these are the derivatives over here. Okay, so we're going to use what we just talked about. So these are f of x. We just said that. And these are f prime x. Okay, so let's start with this one. Now notice that this function is decreasing right there. And so the slope's going to be negative, isn't it? Slope's going to be 0 right here. Then the slope's going to be positive. Then the slope's going to be 0 right here, and then the slope's going to be negative. So what that means is that it starts out with this function decreasing, so that means that the slope's negative. That means the derivative is going to start out negative. So it's going to be, that one starts out negative, and that one starts out negative, because negative means below the x-axis. So which one is it? Well, this one should start out negative, its derivative would start out negative, and then it would be 0. And then it would be positive, and then it would be 0 again. So if we look at this one stays negative all the way to x equals 0. But this one should stay negative only up to right here, and then become positive because the function starts increasing, and then be positive until we get to right here, and then be 0. So this one, the answer to this one is, where do I want to write this? Roman numeral 2. Okay, now B is easy because, you know, the derivative's not going to exist right here or right here. And the derivative is going to be positive right here because we're increasing. So see how this is, and these are little open circles right here because that's where the derivative doesn't exist. And so it starts out positive, and then the function is decreasing. So it's going to be negative, and then the function starts increasing again. So this is the answer for this one. Okay, let's look at this one. Now this one starts out decreasing. And it doesn't matter that this is below the x-axis. What matters is where it's decreasing and where it's increasing. So we're going to have slope's going to be negative right here because it's decreasing. Slope's going to be 0 right here because we got a local min right there. And then the slope's going to be positive here. So it's got to start out negative and then stay negative until we get to 0 and then become positive. So this one matches with number 1. And then this one, of course, you know, we can figure out it's 3 by elimination, but let's just look at this. It's going to be, it's increasing right here. So its slope's going to be positive. Slope's going to be 0. And then slope's going to be negative. And then on and on like that. So if we look at 3, it's going to start out with the slope being positive, so above the x-axis. And then when we get to right here, it's going to be 0. That's where that is. And then it's going to be decreasing until we get to 0. And then it starts increasing again. So the derivative goes above the x-axis until right here, where it starts decreasing again. And then that's where it goes below. So this one's going to be Roman numeral 3. Okay. So that's just matching a function up with its derivative. And that is everything for this section. Okay, class, we're going to have a review session on Thursday. I'm going to send out an announcement and everything. So anyways, I will talk to you. I'll send you an announcement and an email, but I'll talk to you later. Good night.